Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on Advanced Transition Metal Organometallic Chemistry. As a part of our discussion on carbon heteroatom coupling, we have been discussing various types of such reactions, starting with carbon boron coupling, which we had seen hydroboration, and then we have seen CN coupling, in which we have looked into hydroamination as well as arene emination reactions. And proceeding further along the line, we are going to take up another interesting reaction, which is hydrosilylation reaction to be talking about. This hydrosilylation reaction is an addition reaction similar to that of hydroboration or hydroamination reaction, that the addition of silicon hydrogen bonds to alkenes or alkynes. Reaction is addition of silicon hydride hydrogen bonds to alkenes and alkynes to yield alkyl silanes. Now, this is a very general method, most trusted method for preparation of alkyl silanes, and this is exemplified by this reaction, which is given over here, trialkyl silane R3 SiH plus olefin in presence of a catalyst, giving R dashed Si R3. So, similar to the other addition reactions that we have been talking about, hydrosilylation also is an effective method to form carbon silicon bonds by addition of SiH bonds to alkenes and alkynes. And this also serves as a cross linking of silicon polymers. So, one interesting utility is that this reaction serves for cross linking of silicon polymers. This reaction serves for the cross linking of silicon polymers. Now, this hydrosilylation can be done on other unsaturated bonds, like apart from carbon olefinic, it can also be hydrosilylation can be performed on CC, CN, CO, NN, NO and C triple N bonds. So, this is kind of very interesting information that hydrosilylation can be done on CC, CN, CO, CO, NO, NN, CN, and C triple bond N. Can be silylated. For hydrosilylation, the R3 Si group for hydrosilylation the R3 Si group is connected to more electronegative atom, is connected to more electronegative atom. So, in this case for Cn, the Si3 R3 Si would be on nitrogen, for CO the R3 Si would be on oxygen, and the hydrogen will be on carbon, same over here. For NO R3 Si will be on nitrogen, and Cn R3 Si will be on nitrogen. So, this is an interesting observation, and for there is a catalyst which is called Spicer's catalyst, which is the catalyst of choice for or silicon hydrogen addition to non activated double bond, and the complex is H2 PtCl6 dot 6 H2O. This is called Spire catalyst. This is the catalyst is used for SiH addition to non activated C double bond C double bond. And in terms of the olefinic addition, there is another interesting observation is that the terminal alkynes are silylated more readily than the internal olefins. Terminal alkenes silylated more readily than the internal ones, alkenes. Another interesting thing is that the retention of the chiral silyl group retain their configuration. So, retention of configuration is observed in chiral silyl group. So, that is of configuration is observed in chiral silyl group, and the catalytic active species is a palladium 0 species, which is formed from the H2PtCl6 upon reduction with R3SiH, and there is a time required to do for this reaction to happen, and which results in a long induction time. The induction time required for catalysis is due to R3SiH reduction of the precatalyst H2PtCl6 to catalytically active species, which is just bare platinum 0. So, this is an interesting observation that this hydrosilylation using SPI-ER catalyst H2PtCl6 6H2O does not really initiate right from the start. So, there is a time in which the catalyst is formed from the precatalyst, and this the active species is platinum 0, and they are formed by the reduction of this platinum PtCl6H2 by this reducing agent, which is R3Si. So, in that strict sense, that since platinum 0 is carrying out this catalysis, this is not strictly homogeneous catalysis that we have been discussing all the way. So, the catalytic cycle is given as follows: H2PtCl6 in presence of R3SiH giving platinum 0, and this platinum 0 then oxidatively add R3SiH to give this platinum based sigma complex of the type Si R3, and then to this olefin R dust attacks to give this olefin bound complex. The olefin attacks from the external side, Si R3 R dash to give the corresponding product, which is R dash Si R3 along with the regeneration of the platinum 0 species. Now, This hydrosilylation reaction thus composes of three elementary steps. The first is the formation of the sigma complex. To that, second step involves the attack of the olefin to the sigma complex, leading to the elimination of the product in the third step, which is silylated alkane, along with the generation of the platinum. Now, this there are evidence of this formation of the eta 2 coordinated silane complex. So, this was characterized by Kubas, which gives credibility to this computed to this proposed catalytic cycles. So, apart from SPIR catalyst, the other catalyst which can perform hydrosilylation reactions are, besides SPEIER catalyst, R3PH3 rhodium chloride, R3P whole 2 CO rhodium X, and other rhodium 1 and 3 complexes can perform hydrosilylation reaction. Now, so this says that there are one thing crucial about this hydrosilylation reaction in the platinum catalyzed hydrosilylation reaction is the formation of this activated eta 2 silane complex of platinum, which then undergoes this attack from the olefin. The other interesting thing is this, the addition of this platinum silyl hydrogen bond to the product. If one looks at the regiochemistry, and it shows that this is anti-Markovnikov type addition, where the hydrogen ends up on the most substituted carbon, and the silicon ends up on the least substituted carbon. So, this is platinum catalyzed hydrosilylation reaction thus undergoes addition in a anti-Markovnikov fashion, as one may see. So, we had seen these hydrosilylation reactions, how it proceed to give these silyl alkanes, and then we are going to discuss in this context another interesting reaction, which is dehydrogenated coupling. So, dehydrogenated coupling is another kind of reaction using silyl reagents that leads to the formation of silicon-silicon bonds, result in organopolysilanes. So, dehydrogenated coupling results in silicon coupling in organopolysilane. The tendency towards dehydrogenated coupling is as follows. The tendency for dehydrogenated coupling is as follows, which is R Si H3, R2 Si H2 greater than R3 Si H, and the catalyst used in these cases are mixed CP type, very interesting catalyst. They are the catalyst used, common catalyst are mixed CP complexes, mixed CP metal hydride complexes like CP, CP star, zirconium H2 and CP, CP star, zirconium Si, Si Me3 whole 3 Me. Okay. So, these are very common unusual type of complexes. One is CP, CP star zirconium hydride, dihydride, and the other is CP, CP star zirconium Si Me3 whole 3 methyl. So, are used for dehydrogenated coupling, and we are going to take a look at the mechanism for this dehydrogenated coupling, and the active species for these complexes are metal hydride. So, this is the CP2MH where there are 2 cyclopentadienyl ligand, and then the first reaction is the addition of the silane H Si H R H. This silane comes and adds and form the silane comes and adds and form a 4-membered sigma bond transition state. So, this is given as CP2M H Si H R H, then Si H R H whole n minus 1, and these, since it is dehydrogenated coupling, loses hydrogen, this hydrogen H2, and the M over here is titanium, zirconium, hafnium to give this BCP CP2M Si H R H N silane complex, which again reacts with another molecule of H Si H R H N in a similar sigma bond metathesis fashion to give this molecule CP2M Si H R Si R H H n minus 1 H Si H R Si R H H n minus 1. Now, these will eliminate this couple product, which is H Si H R M and Si, which is Si H R N H, along with this generation of the metal hydride bond. So, this is interesting reaction which initiates a condensation mechanism based on sigma bond metathesis, and this is called dehydrosilyle coupling. So, this step is called dehydrosilyle coupling. Dehydrogenated coupling results in the formation of the silicon bond, and by a mechanism which undergoes reactions in which similar to that of the sigma bond metathesis. It also eliminates hydrogen gas as a part of this dehydrogenated coupling. So, with this I am going to conclude today's lecture. Today's lecture had been on hydrosilylation reaction, has mostly been in continuation with our earlier discussions on various kinds of carbon heteroatom bond forming reaction, and in that front we had earlier on discussed CN coupling, then CB coupling in terms of hydrobolation reaction, and in this class we have looked into this hydrosilylation reaction. To recapitulate what has been spoken on today, this hydrosilylation reaction is a very trusted method for producing alkyl silanes, and this is nothing but the addition of SiH bonds to alkanes and alkynes. Hydrosilylation reaction is also has a larger scope and utility, as it can be extended to other carbon heteroatom unsaturated bonds like CO, CN, NN, C double bond N, C triple bond N. All of these moieties can be hydrosilylated, and in such cases it has been found that R3 Si trialkyl silyl moiety resides with the most electronegative atom. As far as the hydrosilylation of non-activated silanes, there are platinum 4 catalyst called Speyer catalyst, whose formula is H2PtCl6 6H2O is the catalyst of choice, and the mechanism sort of have been discussed in detail, and what it turns out that platinum 4 species in Speyer catalyst get reduced to platinum 0 in presence of trialkyl silane, and then this trialkyl silane reacts with this platinum 0 species, active species, to form a sigma complex of this silane, and to which the olefin adds attacks, and then results in the formation of the alkyl silane along with the regeneration of the platinum. This sigma complex has been structurally characterized by Kubus, which sort of give evidence in favor of the proposed catalytic mechanism, and there are other rhodium 1 and rhodium 3 complexes apart from the platinum 4 complex that we just discussed in the context of Speyer catalyst, which can also carry out this hydrosilylation reaction. There are a few things. The hydrosilylation reaction is preferred for terminal olefins as well as opposed to internal olefins, and that the chiral center at the silicon undergo retention in configuration during this hydrosilylation reaction. Going further, we have discussed another important reaction in this context, and this is about dehydrogenated coupling, and the dehydrogenated coupling of this silyl reagent leads to the formation of silicon bond along with the regeneration of hydrogen gas. We have also looked into the mechanism for this dehydrogenated coupling, and we had seen that the mixed BCP complexes of titanium, zirconium, hafnium, either dihydride or silyl methyl derivatives of these complexes are excellent catalyst for this dehydrogenated coupling. As far as the active species for this dehydrogenated coupling are concerned, this is usually BCP metal hydrogen, and then it adds with silane and in a 4 sigma metathesis fashion along with the regeneration of hydrogen gas to give a metal hydride silyl species, which then again adds to a second molecule which sort of in the same sigma metathesis fashion, which sort of leads to the formation of the silane bond, silicon bond, along with the generation of this metal hydride species. So, this also is a 4 elementary step sequence, and this is an interesting catalytic mechanism in which the silicon disilane bonds are being formed. So, with this we come upon to the end of this discussion on hydrosilylation reaction. We have seen that this has been an interesting reaction with lot of scope and the breadth, and also lot of application of this reaction, and as a extension of that, we have looked into dehydrogenated coupling, where silicon bonds are formed in organopolysilines. So, with this I once again thank you for patiently being with me in this class and listening to this lecture, and we are going to take up another new dimension of organometallic catalysis. These are oxidation reactions, particularly olefin oxidation in the next class. So, we have with this hydrosilylation, we have sort of closed our discussion on metal heteroatom bond forming reaction in general, and then move on to the metal organometallic complexes catalyzed oxidation reaction, and to begin with we are going to be looking at olefin oxidation reaction in the next class. Till then, goodbye and thank you.